Section 3.6, molecular compounds. We talked about naming ions and naming ionic compounds. Okay? Now we're going to talk about molecular compounds. The formula has to give us the number of atoms of each element, just like it did for the ionic compound. But now the name needs to also give us that information, because in an ionic compound we had the charges to help us figure out how many of each element. In a molecular compound there are no charges. And we can have lots of different compounds between the same two elements. We just looked at carbon monoxide and carbon dioxide. Look at all the compounds that you can make between nitrogen and oxygen. There's 6 of them. They're all nitrogen and oxygen. We can say, well, yeah, nitrogen forms a -3 ion and oxygen forms a -2 ion. There's no ions in this compound, because how would a -2 and a -3 ion be attracted to each other? They wouldn't. Opposite charges repel. Molecular compounds are composed... Sorry, thank you. Opposite charges attract, like charges repel. I was just testing you to see if you're on your toes. No, I wasn't. Like charges repel. So 2 negative charged ions are not going to form a compound. Nonmetals form compounds by sharing electrons instead of transferring them. How do we identify a molecular compound? Composed of 2 nonmetals. There are molecular compounds that are composed of more than 2 nonmetals. We're not going to learn how to name them in this course. Okay? So our molecular compounds will always be 2 nonmetals. What we do is we use numerical prefixes to indicate how many atoms of each element are present. Here are those numerical prefixes again, and now Nona and Deca are in there for 9 and 10. They probably should have been in before. So that's how we tell how many. And then we also have to decide who goes first. In an ionic compound, I said it's like a wedding invitation. It's always Mr. and Mrs. The metal and then the nonmetal. How do we decide if they're 2 nonmetals? Well, we put the one that's closest to the metals on the periodic table first. So that one is the most metallic-like. Usually that'll be the element with the smallest group number. If you compare like nitrogen and oxygen, well, nitrogen's in group 5A and oxygen's in group 6A. Nitrogen is closer to the metals. The metals are on the left side of the periodic table. Nitrogen is a little more metallic in its character than oxygen is. It's not metal, but it's a little more like it. We're not going to get really hung up on that. But some of you are very curious and want to know, well, why is the carbon first in carbon dioxide? Why? Why isn't dioxygen carbide? Well, it's because we decided to do it this way. So here's the format for the names. You're going to have 2 elements, so there's going to be the name of the first element, and you're going to put a prefix in front of it to say how many there are. And then you're going to have the second element and a prefix in front to say how many atoms of that element. The second element changes its ending to "ide" as if it were an ion, but it isn't. And you might ask, well, why do we do that? It's not an ion. I think it's to avoid the appearance of just a list of elements. The ending of "ide" on the second one helps us to know this is a compound. This prefix for the first element, if there's only one of that first element, then we usually don't put mono. And this falls into that pattern of chemists avoiding the number 1 whenever possible. So if it's, this is carbon monoxide. The mono tells us there's 1 oxygen. It's not monocarbon monoxide. We drop the mono on the first element only. So NO2 is named nitrogen dioxide. There's 1 nitrogen. We leave the mono off. There's 2 oxygens, so the prefix di tells us 2, and then the element name oxygen is changed to oxide. Any questions? There are 2 special compounds that always go by their nicknames, or their common names. H2O and NH3. And you need to know these guys. H2O is water. Right? Most of us know that. It does have a systematic name. It would be dihydrogen monoxide. And, you know, if you have a friend who's alarmist about chemicals, go tell them, hey, I was exposed to dihydrogen monoxide today in chemistry lab. I think I'm going to die. Yeah, you washed your hands. Ooh, scary. Dihydrogen monoxide sounds scary, doesn't it? It's just water. NH3 would be nitrogen trihydride, but we always call it ammonia. Okay, so got to remember those two. So let's name this compound N2O5. What do we call that? Dinitrogen, because there's two nitrogens. Pentaoxide. Or you may also see pentoxide. And that'll come up on the next slide. It would still be the dinitrogen. When we get these double vowels, they get kind of weird looking, and so sometimes we drop the first vowel. Yes?
Is that like the origin of the word toxic? Pentox?
That's a good question. Is this the origin of the word toxic? Because there's toxy in here. No, it's a coincidence. I'll just warn you, students tend to like the system for naming molecular compounds, and then they want to use it for everything. You can only use it if there's two nonmetals. What if we have a name, like phosphorus tribromide, and they say, what's the formula? Well, here's our first element, phosphorus. There's no prefix in front of it, so that means there's one of it. And then the symbol for phosphorus is capital P. Tribromide. Tri means there's three of the bromines. So P, Br, and then a subscript 3. Phosphorus tribromide. Any questions?
PBR. That's gross.
I feel like there's a missing slide, but there doesn't seem to be. Oh well. Another category is acids. There are different definitions for acids. What we're going to use right now is this one. Acids are molecular compounds that release hydrogen ions when dissolved in water. So when we look at the formulas for acids, like HCl, it's composed of two nonmetals. It's not an ionic compound. But when you dissolve it in water, it forms some ions. So there's a separate way of naming acids. We recognize them because acids are composed of hydrogen, which is usually written first in the formula, and one or more nonmetals that are written second. So when you look at a compound's formula, if it starts with H, bingo, it's an acid. The names are even easier to recognize because all the acid names have the word acid in them. Is water an acid? Technically, no. Technically, no. It's not considered an acid. For one thing, you can't dissolve water in water. And the definition here is that when it's dissolved in water, it releases hydrogen ions. Yeah, so technically, no. There are some hydrogen ions present in pure water, but very, very tiny amount. So HCl is an example. It's a molecular compound between hydrogen and chlorine. When you dissolve it in water, it forms hydrogen ions and chloride ions. And this AQ means dissolved in water, aqueous. So if we see just HCl, or perhaps HCl in the gas state, which means this is not dissolved in water, that's pure HCl, then we would name it as a molecular compound. What would the name of HCl as a molecular compound be? Hydrogen chloride or hydrogen monochloride. But when it's an acid, when it's dissolved in water, it's named as an acid. So a compound that will not dissolve in acid is not considered an acid. Characteristics of acids, they have a very sour taste. A lot of the foods that we eat have acids in them. That does not mean that they're dangerous. Your stomach is full of acid. And if it wasn't, you'd have a hard time digesting your food, and your body wouldn't work properly. Acids can dissolve many metals, but not all metals. And their formulas generally start with H. Here's our friend HCl, and here's another one, H2SO4. Starting with an H tells me it's an acid. There are two groups of acids, and they are named in different ways. The oxyacids, here in this flow chart, where's my pointer? There it is. Oxyacids contain oxygen. What many books call the binary acids would be the other acids, the ones without oxygen in them. So different names for the two different categories. So those binary acids. These use a prefix hydro. So here's our picture of the name. Hydro comes first, and then we take that non-metal element that's with the hydrogen and we change the ending of its name to ic. And then we add the word acid at the end. So let's look at an example. Here's HF aqueous. It's dissolved in water, so we're going to name it as an acid. There's just hydrogen and fluorine, there's no oxygen. So we're going to use the rules that I just talked about. So we start with this prefix hydro, and then fluorine becomes fluoric. So fluoric, and then the word acid. So this is hydrofluoric acid. Yes?
Where's the AQ on the side?
The AQ means it's dissolved in water.
Okay.
That means we name it as an acid. I won't try to trick you on that, but there could be worksheets or something that do try to trick you. If it says gas, then you'd have to name it as a molecular compound, and it would be hydrogen monofluoride. But I'm not going to try to do that.
Couldn't you just say hydrofluoride instead of hydrogen?
No, you couldn't say hydrofluoride because that doesn't fall in the system of naming. Somebody's got their bass speakers way too loud.
What? There must be
Right? What? I mean, they're shaking the hoods.
all the police.
That's more distracting than the trains.
On his bicycle.
Yeah, on his bicycle. So we have a system so that things are uniform. And students sometimes get irritated and frustrated with how picky the system is. But when a system is not picky and consistent, then that gets annoying too. Like the English language, right? If you've studied or if you know another language, Spanish or German or something, you know that English is much more irregular. There's so many exceptions to all kinds of things when you conjugate verbs and past tenses and all sorts of things. It becomes more difficult. A language where everything is consistent is easier to learn. And the nomenclature is very consistent. And so sometimes it's annoying, but we just have to go with that. So with the oxyacids, they have oxygen in them. They're going to be hydrogen and one of those oxyanions, like nitrate or sulfate or phosphite or something. And so what we do to name it as an acid, we look at the ending of the oxyanion. If it's ate, we change it to ic. If it's ite, we change it to us. And then you add the word acid. So we have to remember which goes with which. And that can be a problem sometimes. So there's a silly sentence. There are other ones, but this is the one I use. Rick ate him before he could bite us. And don't think too long about the sentence and about who he might be and why we would eat him. Rick ate him before he could bite us. It's just silly, and that helps us to remember it. Oops, that's not what I meant to do. So, ite and us go together. Ick and ate go together. So we have two pairs of things and we have to remember the correlation. So let's do an example. Name HNO2. Name HNO2 aqueous. So we're going to name this as an acid. It starts with H and it's dissolved in water. We look at it and we see, oh, it's got oxygen in it. We have to name it as an oxyacid. We need to figure out the name of the oxyanion that is present in here. So cover up the H. What's left? We've got NO2. NO2 is an oxyanion. It has a special name. Nitrite. So this is nitrite. So I'm going to write that down. We've got NO2. And this is nitrite. So we're going to change this ending of ite to what? Us. So this becomes nitrous acid. HNO2 aqueous is nitrous acid. Any questions?
So you don't even worry about the hydrogen at all?
We don't have to specify the hydrogen. The word acid tells us that there's hydrogen on it. So the binary acids use the prefix hydro. The oxyacids do not use the prefix hydro. Let's look at how we would write the formula for perchloric acid. Well, does the name start with hydro? No, it doesn't. That tells us it's an oxyacid. So I need to take this name, perchloric, and change the ending back to the name of the oxyanion. Perchlorate, because ate and ick go together. Rick ate. So this ick tells me this is from perchlorate. So I'm going to write the formula for perchlorate ion. ClO4 minus. Got a lot of questions on the 1-minute papers about not understanding the names of the polyatomic ions. There's not a lot to understand. You just have to memorize them. That's it. I'm sorry. So this is perchlorate because we decided to call it that. And then the other part of the acid is hydrogen ion. Hydrogen is in group 1A in the periodic table. It's not a metal. It's the baby brother of the element family. He's over there. The reason he's over there is the most common ion that he forms, or she really, is a +1 ion. So here we have a +1, and chlorate is -1, and we use these charges to help us put it together. And so the formula for perchloric acid is just going to be HClO4, and then we really should put AQ in parentheses. Any questions? So this is kind of review. When the name ends in acid, it's an acid, and that means that the formula starts with H. You write the formula as if it were ionic, even though it's actually molecular. The hydro prefix means it's a binary acid. If there's no prefix, that tells us it's an oxyacid. For oxyacids, the ick and ate endings go together, and the us and the ite endings go together. Any questions? Here's some extra examples. Write formulas for these acids. Hydrocyanic acid. So what does the prefix hydro tell us? Binary acid, right? Okay, so then we're looking at cyanic. That's supposed to be an element, right? Is there an element that's like that? Cyanide. So here's cyanide. Well, okay, we'll go with that. And how many hydrogens would it need? just the one, right? So the formula for this is HCN aqueous.
The first one's the only one with hydro. Does that mean that's the only binary acid?
Yeah, of these three examples, the first one is the only one that starts with hydro. It's the only binary acid. And the other two, because they don't start with hydro, must be oxyacids. This acid right here is why I don't like the term binary acid. How many elements are in that? 3. That's not 2. I prefer to think of them as oxyacids and not oxyacids. But your book calls them binary. So
Wait, why is it CN? I'm sorry. Why is
CN is cyanide.
it just
And it is cyanide because that's what we decided to call it.
Would the
It's
be lowercase? Because that makes it mean carbon nitrogen.
It is carbon and nitrogen. It's a polyatomic ion.
Oh, gotcha.
Yeah, it's a polyatomic ion between carbon and nitrogen. It doesn't fall into the category of an oxyacid because there's no oxygen in it, but it is a polyatomic ion. And so he's kind of in no man's land here. So he got stuck in with the binary acids. That's the only example I know of. So let's look at this one. Phosphoric acid. Lack of the hydro prefix tells us this is an oxyacid. So we name this by changing this ic ending to what? 8. So this must be phosphate. And then we need the formula for phosphate. So we pull this up from our memory banks in our heads. PO4 3-, and it's going to have hydrogen with it. So what's the formula? H3PO4. It needs to be a neutral compound. There's an ion that's HPO4 2-, but that's not an acid. It's not named as an acid. It's an ion. And then we should put AQ. H3PO4. Any questions?
So it's really easy, like once you figure out how to start naming them and then to make it an acid, you put the AQ.
Yes. Once you figure it out, it's really easy. It's the figuring it out part that people have problems with. Once you see the pattern, you're like, oh, I get it now. It's like, when you're trying to look at one of those pictures and you can't see the image in it, and somebody tells you what it is and kind of points it out with their finger, and then you're like, oh, well, yeah, it's really clear now, but I couldn't see it before. Okay, this third one, hypochlorous acid. Hypochlorite. Now, hypo and hydro kind of look the same, but they're not the same. Us becomes ite. So this is from the hypochlorite ion, which has what formula? ClO-. And that needs to be combined with hydrogen ion, because all acids have hydrogen ion. There's a -1 charge, and so we just need one hydrogen, HClO. Aqueous. Any questions? Acid rain is a problem. Some of the pollutants that are listed here that come from combustion and other sources will form acids when mixed with water. And there's water in the air and up in the clouds. And so they'll form acids, and then they come down with the rain, and they can cause a lot of damage to plants. They can kill forests. And here are 2 statues. This one apparently was like under a roof, and so it hasn't gotten rained on as much as the other one. They were identical to start with, and this is, it's just being eaten away by the rain.
Do you need to memorize those pollutants?
No. No, this is one of those slides that I think there's a lot more about it in your textbook, and I think it's good to mention these things because it helps us to understand how chemistry is relevant to everyday life and why understanding chemistry is important. But I'm not going to test you on that.